This is Sam Daulton. Today I'll be presenting our work on parallel Bayesian optimization of multiple noisy objectives with expected hypervolume improvement. This is joint work with Max Balandat and Eytan Bakshy. We consider the problem of multi-objective optimization, where the goal is to optimize a vector-valued black box function that is expensive to evaluate and does not provide gradient information. Bayesian optimization is a popular sample-efficient approach for optimizing such functions. It relies on a probabilistic surrogate model and an acquisition function to sequentially select new candidate points to evaluate on the black box function. The new observations are incorporated into the dataset and used to update the surrogate model. While the black box function is expensive to evaluate, the surrogate model is relatively cheap to evaluate and provides gradient information which can be used to efficiently optimize the acquisition function. In multi-objective optimization, there typically is no single best solution. Rather, the goal is to identify the Pareto Frontier of optimal trade-offs between the objectives, such that improving any objective means degrading another. Hypervolume is a common metric that is used to assess the quality of a Pareto Frontier and is defined as the volume that is dominated by the Pareto Frontier and bounded from below by a reference point. Typically, the reference point is selected by the decision maker according to their preferences. The quality of a new point in terms of its contribution to the current Pareto Frontier is often assessed in terms of the hypervolume improvement, which is the incremental hypervolume if that point were to be added to the Pareto Frontier. Hypervolume improvement is often computed using box decompositions, where the space that is not dominated by the Pareto Frontier is decomposed, partitioned, into a set of axis-aligned hyperrectangles. The hypervolume improvement can then be computed in a piecewise fashion. Although the function values at a new point are typically unknown, the probabilistic surrogate model provides a posterior distribution over what the function values are given the observed data. Using this posterior distribution, a common acquisition function in multi-objective Bayesian optimization is the expected hypervolume improvement. Although a closed-form expression for expected hypervolume improvement exists in the sequential selection case, a common approach for computing expected hypervolume improvement is to approximate it with Monte Carlo integration. Recent work has extended expected hypervolume improvement to the parallel setting where multiple points are selected simultaneously. In this case, the acquisition function is the joint hypervolume improvement of the multiple points. This joint hypervolume improvement has been computed previously using the inclusion-exclusion principle. We now arrive at the two fundamental limitations of expected hypervolume improvement. The first is that no previous work accounts for observation noise. Expected hypervolume improvement assumes that the objectives are observed without observation noise. In the case that the objectives are observed with observation noise, expected hypervolume improvement can perform poorly. Another limitation of expected hypervolume improvement is that the parallel variant scales exponentially with the batch size due to the use of the inclusion-exclusion principle. This limits its applicability to the small batch regime. To tackle these limitations, we propose a novel acquisition function, noisy expected hypervolume improvement. In the noisy setting, where the observations are corrupted with noise, the observed Pareto Frontier can be quite misleading, and ignoring observation noise can have undesired consequences. To handle observation noise, we propose to integrate over the in-sample function values. In a sense, this is integrating over what the Pareto Frontier is across the in-sample points. This expectation can be computed using Monte Carlo samples from the joint posterior over the new point and the previously evaluated points. In the figure on the right, each colored line corresponds to a Pareto frontier under one joint posterior sample. The red star corresponds to the new candidate point. Taking the average of the shaded region, the hypervolume improvement, we can compute a Monte Carlo estimator of the noisy expected hypervolume improvement. Now, computing the hypervolume improvement under each posterior sample requires a box decomposition given the sampled Pareto frontier. Although there has been significant progress on efficient algorithms for computing box decompositions remained expensive to compute. Therefore, it would be infeasible to recompute these box decompositions every time the acquisition function is computed. To handle this issue, we propose to fix the sampled function values at the in-sample points. This enables us to compute the box decompositions upfront once per BO iteration. We cache those box decompositions and use them for subsequent acquisition function evaluations. We refer to this concept as cached box decompositions, or CBD. NeHVI can be efficiently optimized using exact sample path gradients of the MC estimator. Using sample average approximation, we provide a theoretical guarantee that optimizing the MC estimator will recover an optimizer of the true NeHVI in the limit. We'll now show how CBD can be used for efficient large batch selection. First, recall that previous work has shown that sequential greedy batch selection leads to better closed-loop performance than joint batch selection. In the sequential greedy setting, we first select a design X1 and fix X1 when we select X2. Therefore, we can incorporate sampled function values for the design X1 into our cached box decompositions. This allows us to only compute the incremental noisy expected hypervolume improvement from a new design X2. If we select candidates in this way, we can decompose the joint noisy expected hypervolume improvement into the noisy expected hypervolume improvement from the new candidate and the noisy expected hypervolume improvement from the previously selected points. This term on the right is therefore a constant, and we only need to compute the incremental noisy expected hypervolume improvement. This reduces the complexity from exponential to polynomial in the batch size, enabling NeHVI to scale to the large batch regime using CBD. We demonstrate that noisy expected hypervolume improvement achieves state-of-the-art performance on a variety of sequential and batch noisy problems. In the batch regime, we show that NeHVI performs best regardless of the level of parallelism. Our implementations are available in open source in Blowtorch and Axe. Please check out these GitHub repositories and our tutorial, and check out our poster and paper for more information. Thank you.